Okay, now we have MAT 2020 question 2. It has been a while since I last uploaded some question 2, so good chance to do some long questions instead of always doing multiple choice questions. So let's see. The functions f of n and g of n are defined for positive integers n as follows. So fn is 2n plus 1, gn is 4n. Great. And this question is about the set S of positive integers that can be achieved by applying some f's and g's to the number 1. That's quite important. You know, you can only apply a certain sequence of f's and g's to number 1 only. Right? And they gave you some examples. Brilliant. Okay, so let's dive straight into the questions. Part 1, write out the binary expansion of 100. Okay, so I think that's quite irrelevant to the, to the background, right? So what do we think? Binary expansion of 100. So we've got to find a power of 2, which is, the largest power of 2, which is within 100, right? And what would that be? Have a think. And that would be 64. Yeah, 64 is like 2 to the 6, I suppose. Yeah. Okay, so how many are we left with? We're left with 36, right? Because 100 minus 64 is 36. So I'm going to find a power of 2, which is within 36, which is 32. Yeah, so 2 to the 5. And I'm left with 4, so 4 is just 2 squared. Perfect. So it'll be 2 to the 6 plus 2 to the 5 plus 2 squared. That's the binary expansion of 100. All right. Okay. Fine, next bit then. Show that 100 is an S by describing explicitly a combination of F's and G's that achieves 100. Okay, so how do we do this? Well, we've got to observe what's going on here. What's going on in the binary expansion, sorry. Yeah. Okay, so we start from 1, right? So we have this sort of 2 to the 6 plus 2 to the 5 structure here, right? So these things, they are power of 2's which differ by 1, right? So it definitely comes from an F, first of all, right? It definitely comes from an F because the F is like a 2n plus 1, right? So you multiply by 2 and then you plus 1, right? So the powers of 2 differ by 1 here, right? This is 2 to 1 and this is 2 to 0, of course. Yeah. So therefore, the first application must be an F. Must be an F. Yeah, that gives you what? That gives you 2. So where should I write this? This gives you 2 to the, so 2 times 2 to the 0 plus 1. That's me being very explicit. Yeah, or maybe 2 to the 0 here. Yeah, so that gives me 2 to the 1 plus 2 to the 0. Yeah, so this is the basis for us getting 2 to the 6 plus 2 to the 5. Okay. All right, now I have to construct the 2 squared, right? I have to construct the 2 squared, but before that, I got to make sure that, my 2 to 1 and 2 to 0 actually go up the powers, right? Because 5 and 2, the power of 5 and the power of 2, they're quite different. Okay, so let's apply g onto it, such that I can raise it up the powers. So I apply g to it, which becomes 2 cubed plus 2 squared. Okay, now, is this the moment that we apply f? Or should we continue with g? Now, this is the moment that we apply f, right? Because if you think of it, if you apply f, then what do you get? Then you get 2 to the 4 plus 2 cubed, and then plus 1. Right? So now, you see, these powers differ by 3. The 2 to the 3 and the 1, which is 2 to the 0, the powers differ by 3. Right? So brilliant. Now I've constructed what I wanted, so I'm going to add an f in front. And lastly, of course, I'm going to multiply by g, such that I get 2 to the 6 plus 2 to the 5 plus 2 squared, as required. All right, so the key thing is to observe the differences between the powers and then decide which functions to apply. Yeah, that's what I would do. All right, look at the powers and then decide. Okay, part 3 then. Show that 200 is not an S. I suppose I should get rid of the writing before I do anything to make myself some space. Okay, show that 200 is not an S. What do I do? So the key observation actually here is that, remember, f was equal to 2n plus 1. Yeah, the output of f is odd. Right, the output of f is odd. Okay, how about g? The output of g is 4n, which is even, right? That's a key observation. And, we could go even further than even. Is even and a multiple of 4. It must be a multiple of 4. Okay, so show that 200 is not an S. Okay, So where must 200 have come from? It must have came from G, right? Because 200 is not odd, right? So it must be G of 50. Yeah, if 200 were in S, or was in S, I suppose, I don't know about the subjunctive, then G of 50 must be there, right? It can't come from F, right? G of 50. Okay, so where does 50 come from? Well, it can't come from the F, right? Because F is odd, and the output of F is odd, so it doesn't come from F. How about G? Does it come from G? Well, not really, right? Because 50 is also not the multiple of 4. Yeah, so that's why 200 is not in S, because 50 cannot have come from anywhere. Yeah. Okay, cool. Now, part 4 then. Show if n is in S, then there's only one combination of applying F's and G's in order to achieve n. Okay, so it's nice that we're given, so the n is always in S. All right, that's an assumption. So what can we do? Right, if we already know beforehand that n must be in S, then you can do the same trick as part 3, can't you? Right, you can think backwards. So, well, if the number is odd, then you're gonna apply F to it and then get a new number, right? If the number was even and a multiple of 4, then you can apply G to it, right? For example, let's use the example 67, right? Just to illustrate. So 67, you would think, okay, 67 is odd, right? So therefore, then I'm gonna apply F first, right? So it must be F of, what was it? F of 33. Yeah, F of 33. Okay, 33 is odd, right? So I continue. This will be F of 16. Yeah, F of 16. Oh, sorry, F of 16, I suppose. Yeah, because I've done F 2 times already. And now 16 is multiple of 4, so this becomes F of G of 4. And then lastly, you get F of G of 1. All right, so that is exactly what the original example gives you on top. Yeah, so that's how you can deduce how to apply the F's and G's, and there's only one way, right? Because there's no way that a number is simultaneously odd and even. Impossible, right? So it's clear that there's only one way. Okay, part 5 then. Let UK be a number of elements of n that lie in the range 2 to k and 2 to k plus 1. Show that that's true for k greater or equal to 0. Cool. Okay, so it's asking me what happens if UK plus 2, right? So UK plus 2 is the range 2 to k plus 2 less than or equal to n less than 2 to the k plus 3. Yeah. Okay. So what can I do? What can I do? Well, for example, UK is the stuff within there, right? So what can I do to UK such that it brings me to the range that I want? How can I go from UK to UK plus 2? Well, what I did basically is multiply the whole inequality by 4, right? If 2 to k goes to 2 to k plus 2, that's essentially multiplying by 4. So if I apply G to all the elements in U of k, then great. I get something in U to the k plus 2. Right? I get something in there. But there's also contribution from the U to k plus 1. Right? Because if I apply F onto if I apply F onto UK plus 1, apply F onto the elements of UK plus 1, I suppose, then you also land on the range 2 to k plus 2 less than or equal to n less than 2 to k plus 3. Okay, so if I apply F to the UK plus 1 and if I apply G to UK, I both get numbers in UK plus 2. Yeah. Of course, that builds on the assumption that UK plus 1 and UK, they contain elements of S, right? So the key assumption is that it's within S already. So this equality would hold true. Yeah? This recurrence relationship holds true because UK plus 2 must contain elements from UK plus 1 and UK. All right, it can't come from like UK minus 3, for example, right? There's no F or G such that it brings something from k minus 3 up until k plus 2 straight away. Yeah, it doesn't make sense. Okay, so these are the only two groups possible. All right, so that is part 5. And how about part 6 then? What can we do? Let SK be a number of elements of n, a number of elements n of S that lie in the range 1 and 2 to k plus 1, and show that that relationship is true. Okay, this is very similar to part 5, right? I mean, the only difference is that, okay, could we see? Maybe we can't see. Let me scroll down a bit. So the only difference is that there's a plus 1 here, there's a plus 1 here, and also the range is different. And these are only two different things. Okay, so what can we do? What can we do? Again, the logic is the same, right? Okay, so again, you got to think sk plus 2, where could it come from, right? So if I apply f to sk plus 1, then again, I'll get sk plus 2, right? I mean, it's the same logic as the u's, right? But then the difference here is that if you apply f to sk plus 1, you can't really get the element 1 in sk plus 2. Like, you can't get 1 here. Yeah, if you think of the range, you can't get 1, right? Because once you multiply the range by 2 here, then you get 2 like this, right? So you can't really get the number 1 anymore. Yeah, and also if you apply g, onto sk, again, it doesn't give you the 1 again. It doesn't give you the number 1 at all. Yeah. So the only thing we could do is we got to add 1 behind, all right? Because we got to include the number 1, right? The number 1 is in sk plus 2 as well. So conclusion, sk plus 2 equals sk plus 1 plus sk plus 1, because sk plus 1, if you apply f to them, it gets you into sk plus 2. Yeah. If you apply g to sk, it gets you into sk plus 2. And you can't exclude the number 1, right? The number 1 itself, which can be obtained without doing any functions, is within the group sk plus 2 as well. So therefore, you're going to add 1 to take care of that. So that gives you the full expression. All right, okay, that concludes question 2.